Yes, that's actually a paper here's a camera. We presented at ASE 2020. We have the paper online, we have the project online, the artifact is there, we even have a pull request, but it's not completely identical to what we use on the paper, but that source is also available, so you can play with that one. It's the second day of the symbolic execution workshop, so I think it's a good idea to actually introduce symbolic execution, right? So what we have in symbolic execution, of course, we explore program path, right? And the state encapsulates a path, right? It has the stack and the path condition, the program count, and all this stuff. And as a mental model, a state was program path. So in standard symbolic execution, we hit a symbolic branch. We use an SMT solver to check both branches if they're feasible with respect to states. So we now have two states. We have two states, so we have to select one of those states with a searcher, or what we call in the paper, search heuristic, exploration strategy, and so on. So when we create more and more states in memory, or not just a single one, like in colic execution, we call it, at least in our EGT style, symbolic execution from the execution generated test cases paper. So when you read it in our papers, that's what we call EGT style. So that's also what KLEE does. But the thing is, when you get more and more states, especially with the default search heuristic, you have such a huge state that at some point that you have to terminate states. And in KLEE, we randomly select states currently, at least upstream. And then we terminate them. And that means all the subtrees and the paths we could explore basically lost, unless we use memorization to resume such executions. And that's what was something I presented last year here at the workshop and at Easter also 2020. But I don't want to talk about that one. I just want to show you one figure. What we did in the paper basically is we measured how many states are actually terminated early due to memory pressure. So we took 87 core utils and ran KLEE with the default search heuristic for 2 hours with, I think, 2 GB memory limit. And what you can see is that for many of those core utils, we kill more than 80% of all created paths, right? Just due to memory pressure. You can increase it to 10 GB, it looks almost the same. So when you think about it, that's quite wasteful, right? Because all those feasibility checks we did, right, are useless. We just terminate the state. So that's where basically pending constraints come into play. What we do is we reverse 2 operations. So first, we fork, and then we use a fast but incomplete solver to solve or to do the feasibility checks. As that one is incomplete, we have basically 2 ways that we need to handle. So the first one is our incomplete solver thus that path is feasible, and then we continue as usual symbolic execution. And then we have cases where we just don't know if the path is feasible or infeasible. And in that case, we do not alter the path condition. We just take the constraint and append it as a pending constraint. We just don't know. And then that state becomes a pending state. So we divide our state space in 2 classes. We have pending states and we have feasible states. So of course, we have to select states, and what we do is we just select states from the feasible ones, and when that is exhausted, we start picking ones from the pending state set. And here we use the expensive SMT solver check and solve the pending constraints and check, is it feasible or infeasible? If it's infeasible, we delete it. If it's feasible, it goes into the feasible state set, and we continue. So no, that's the fancy part. What is this fast incomplete solver, or what does it return? And the thing with the solver is it returns feasible for all paths that are known to be feasible. Sounds weird, right? So the thing is, when is a path feasible? That's pretty easy. When we have a concrete assignment for our symbolic values that satisfy the path condition, right? And there are 2 cases where that happens. Either we have seeds, concrete input test cases, production data, fuzzing inputs, whatever. or we have cached assignments. What are those cached assignments? So we have to look at the KLEE's solver chain. KLEE itself doesn't talk directly to an SMP solver like Z3 or SDP, right? We have some stages and before. The independent solver removes all the stuff that we don't need to solve a specific query. Let's say we solve for A less than B, then we remove everything related to C if there's no closure. Then we have a simple query cache that just takes a query and maps it to feasible or infeasible. If you don't have a hit here, we use a counterexample cache. And the counterexample cache basically has all the assignments. We use our symbolic variables. We try to map them and find the mapping. And when we find a feasible one, we return feasible. So we still don't have to talk to the SMP solver. If we have to cache it here, we actually go into the SMP solver, we query it, typically for satisfiability, but not just for satisfiability, we ask basically for witness values. And those models end up in the counterexample cache. So what's the fast incomplete solver? We just stop here. That's it, basically. And that has a nice, basically, side effect. We can implement seeding quite efficiently. We just put the assignment in the beginning in that cache, and we get seeding for free. Okay. So let's start with an example just to show you how that works. This is a classical example from the KLEE repository. We have a getSign function. It returns -1 for negative numbers, 1 for positive numbers, or 0 for 0. We start with a call. X is symbolic. We use the first statement, that's fine. We assign -1 to R. And then we hit the first symbolic branch instruction. So in classical symbolic execution, we would just solve or check the visibility of both branches. Here we don't. We just fork, and now we have 2 pending states because our counterexample cache on the bottom corner is empty. Okay, so we have no feasible states, and the searcher picks some pending state. We revive it. We solve the constraint with SMT solver. We get an assignment on our counterexample cache, and we continue. And the next if statement, no, we have 1 feasible state now, so we always select that 1 feasible state. We continue. We read the if statement. As you can see, we can reuse that assignment, right? We have immediately a solution without querying the solver here, right? So we are done. We finish this pass. Now we are left with 2 pending states. We revive one by querying the SMT solver, get an assignment, use that one. Same on the right. We revive that pending state. We reuse that result in the feasible state. And the last one is infeasible. When you stop now, you see the assignments, you see the tree. It's exactly, or it looks exactly like normal symbolic execution, right? It's just we turn towards the order and we change basically the searcher what states are selected. In order to get an intuition why that is actually useful, let's look at a different example. You don't have to read the code. What we basically do is we reverse an MD5 hash. That's quite expensive on an 8-byte buffer. And we put an assignment, 1 concrete assignment, into our counterexample cache. So that's a seed example, but it's, as I showed you, it's basically the same as normal, as we would get the result from a solver. It's just different. So let's assume that that tree is again the tree for that MD5 computation, right? And the computation in the counterexample cache follows that red path. So we use the seeding mode in vanilla KLEE, the original one, or upstream KLEE, and we use it here, the new one for pending constraints. So we start, and in pending constraints, we have 1 solution, and we have 1 feasible state. We drive it to the end. We're here. 0 solver calls. In vanilla KLEE, we start with that path, but in upstream KLEE, we always check, at least for now, the neighboring path, right? So here is the first solver call. With the first solver call on the pending side, we just pick a pending state somewhere, here the same branch and drive it to the end. So we are much deeper in the code. And that happens when we follow that path for the seed, look to the right side to vanilla. We reach the end of the seed with 8 solver calls. Okay? But now compared to the pending side, we're much deeper in the code and we executed way more instructions, right? With the same number of solver calls. So why pending constraints? We make much more efficient use of the solver solutions. So we execute more instructions per query. We spend less time solving infeasible query. And if you don't believe me, we have a figure in the paper. We measured it actually. And you can see that the greenish ones, the pending implementation, has much fewer or solves fewer infeasible queries than upstream KLEE. And there's one exception here, SQLite, but actually we are better in that case as well because the absolute solver time is much lower. So we don't waste that much time. We evaluated the thing on 8 hard applications, at least hard for symbolic execution, TCP dump, SQLite, data mesh, M4, and so on, in 2-hour runs. And we also did a 24-hour SQLite study. And as you can see, so we use 3 standard strategies here. There's nothing modified. You can see the random pass here, as we have huge outliers. So SQLite works much better, for instance. TCP dump works better, make works better, right? And so on average across those benchmarks, we got 35% more coverage with random pass, 34% with less bias search, and 24% with DFS. There's also when you, where was it? Here, you can see that sometimes you also have complementarity in the combined coverage results. The seeded version is they're closer to each other, of course, because we follow a path and then explore from that path, right? And so we only get 25, 30, and 32% MAC coverage. And again, some cases work really well if you look at image magic, for instance, and again, SQLite. There's one outlier, I think, where is it? M4, for instance, and M4 resolves a lot of symbolic pointers, and the pending constraint doesn't really help. We just have the overhead of the extended state set. So that's a 24-hour run SQLite, and you can see we have a much steeper curve with pending constraints, so we get much earlier, much better coverage. And even more interesting is the seed version. So we apply a seed that has roughly 37,000 instructions, and you can see, due to the safety checks and the neighboring paths, upstream KLEE is not even able to follow that seed in 24 hours, right? Whereas pending constraints actually needs, I don't know what, 3 hours to finish that one due to the pending, to the safety checks, division by 0, out-of-bound checks. That's the expensive part here. And then we have pending states that don't bring you coverage, but it actually gets lucky, and you see this is a much higher curve. That's it from my side, basically. Thanks.